okay, now that we've worked through what it means to be one-to-one, how to determine if a function is one-to-one or not, now we can really get into what we want to work on here, our inverse functions. So here the definition of an inverse function starts with let f be a one-to-one function. And that's why we took all the time to deal with one-to-one, because the whole idea about inverses, what we really want to do, does not work for functions that aren't one-to-one. So we need to be absolutely sure that the functions that we're dealing with are one-to-one. So let f be a one-to-one function with a domain D and a range R. And so here, once again, D is a capital letter, R is a capital letter. We're using set notation. They're not individual numbers. They're sets of numbers, the collection of all the inputs and the collection of all the outputs. So f is a function with a domain D and a range R. All right? So that's our setup, the condition there. Then it would say a function, let me spell it right, a function G is the inverse of f, provided that the following conditions are met. F of x equals y if and only if g of y equals x for every x in D and for every y in R. So I'm using a little bit of notation there. Remember that upside down capital A means for every, and we're saying x, individual element x, that is in the set D, and for every, upside down capital A, y, individual y's, that are elements of the overall set R. So it goes back to that idea of undoing. If I put a value of x into the function f, I will get out a y. But if I then take that y and I put it into the function g, I'll get the x back that I started with. And that goes all the way back to this picture that we started with here, where if I erase these, this mess that we were talking about when we were talking about domains and ranges. But the big idea, once again, is still that if I take some x, put it into f, get out a y, take that y, the whole idea of the inverse is that undoing, and I get my x back. And so I'm going to write that statement down again that we had in our definition, that f of x equals y if and only if g of y equals x. So this part of the picture is this part of the statement. And let me get a good color here. This part of the picture, note that they overlap. This part of the picture is this. So there is that overlapping there, and that y playing that dual role. So that's our formal definition now. Remember, last video and in class we've been talking very informally about this, but now we are formalizing this into this definition. Now, I do want to point out that it is important. The for every is very important. This has to be true all the time. It can't be part of the time. You know, it has to be for every single x and every single y. It has to work all the time, all the time, all the time. I cannot emphasize that enough. So that's our formal definition of an inverse function. Now a little bit about notation for an inverse function. What we would normally say is instead of calling it g of x, so well, that's not a good color there. Let me choose a different one here. If we have some function f of x, then the inverse is usually called and written as f inverse of x. Now that's a notational thing we have to be careful for, that this -1 is not an exponent. It's not a -1 exponent. It's a notation. That just means f inverse. If I wanted to have a negative exponent, I would write f of x equals, f of x with a -1. Here, color issues again, f of x to the -1. And that is equal to 1 over f of x with our normal exponent definition. So in this position, it's an exponent. But in this position, it is not an exponent. It is a notation to indicate the inverse function. So from my previous slide, where we would say that f of x equals y if and only if g of y equals x. This g of y is normally written as f inverse of x. And that can get pretty tricky because we are now using x. We're now using x to mean two different things. This x is x input into f. But this x right here is actually this y. And that gets a little tricky with the notation. So we use x for both of them just because notation says we use x as the input into our function. But we have to understand that this x is an element of the set D, but this x is an element of the set R. We're not used to saying that. So we'll work on that in class, continue talking about it. I'll ask you questions to make sure you understand that as we work our way through it. So that's how we write some of those inverse stuff. And just an introduction there. And the last thing I want to talk about in this video is the theorem on inverse functions. And what this says here, and maybe I'll change this color to make it so we can see it a little bit better, is that what's very important about this what we're saying here is that this is what you're going to use to show that two functions are inverses of each other. When we are given two functions and we want to demonstrate are they inverses of each other or not, we want to prove it, this is what we're going to use. We're going to start with the same let. Let f be a 1, 2, 1 function with a domain D and a range R. Then we'd say if G is a function. Now remember we said that the inverses have to be functions as well. So I'm very specific here to use that word function. If G is a function with domain R and range D, we've been talking about this, that flipped relationship there. Then, if-then statements, it's a theorem. G is the inverse if the following conditions are met. Now, note the plurality of it. And it is indeed, you need both conditions to be met to have this. So our first condition says that G of f of x equals x for every x in D. And basically, that's just your composition of functions. And that's going back to our picture of our boxes. If I take an x, put into the function f, get an answer for this. Take that answer, put it into the function g. G would undo what f did and give me my x back. So that's just stating that. So that's about saying that the function g undoes the function f. But we also need f to undo g, which would look like this. If I take a value x, well actually we'll go with a y here to keep it a little cleaner, I suppose. We'll go with a y there. If I take a y, put it into g, get an answer. Take a y, put it into g, get an answer. Put that answer into f, I get my y back. Remember that the statement said they need to undo each other. It is not enough that G undoes F. I also need F to undo G. Now that has to be true once again in all cases. So it's almost like we have four things to worry about. That we need this, but we can't forget that it has to be true all the time. There's two conditions, but each condition has two pieces to it. Okay? So that's the definition. That's the theorem that we are going to use to demonstrate that two functions are inverses of each other. So make sure you have this, study it, know it, understand it, be able to reference it. When you come to class, we're just going to jump right into actually doing that. This is going to be our first example in class. Show that f of x and g of x are inverses of each other, and we're going to use that theorem to do that. Okay? See you guys in class.